let's look at another example of solving an optimization problem using these ideas from calculus that we've worked out. So suppose we're on a straight stretch of beach near an island 200 meters offshore that we want to get out to, and the island is 1,000 meters along the shore from where we're currently standing. If we can walk at 2 meters per second and swim at 4/5 meters per second, this is 0.8 meters per second, where should we start swimming to minimize the time it takes to reach the island? So you can see, since we're trying to minimize something, this is an optimization problem. We're trying to find a minimum value, and the thing we're trying to minimize is time. So what we're going to have to do is somehow express the time that it takes as a function of something. To understand what the independent variable should be, maybe we should draw a sketch of the geometric situation here. So let's see, here's our straight shoreline. Let's say that we start over here. There's us. And the island is out here somewhere. And it's 200 meters offshore and 1,000 meters along the shore. Okay. So how do we get out to the island? Well, we're going to walk part of the way, I guess. And then at some point, we're going to have to get into the water and swim the rest of the way. And we might as well swim in a straight line. So to decide on how we're going to get out to the island, what we have to choose is, where is this point where we get in the water? Where is this takeoff point? To describe where this takeoff point is, well, we could measure that from anywhere. And sort of the two obvious choices are, we should either measure it from where we start, or we should measure it from this right-hand end here, this spot on the beach that's closest to the island. And I mean, I can tell that at some point I'm going to need to know this blue distance, so I'm going to have to use the distance formula, and that's going to involve a square root. And it would be nicest if the stuff inside the square root were as simple as possible. And so it would be nice to name this distance, or call this distance our independent variable, instead of the red distance. So I'm going to call this distance x. That makes this red distance to the left just 1,000 minus x, since it's the distance from us to this closest point minus the distance x. So 1,000 minus x. Okay. So now we can start to work on, we've identified what our independent variable is, what the quantity is that we can control. So now let's write the time that it takes as a function of that variable. Well, the time that it takes is going to be the time that we spend walking plus the time that it takes swimming. Okay, well, how long does it take to do this walking leg of the trip? Well, in general, if you're traveling at a constant speed, the distance that you cover is the speed times the time that it takes to, times the time that you travel. So we want to find the time, so we need to just solve this for t. So t is the distance over s. All right, so when we're walking, as we're walking, we're traveling at a constant 2 meters per second. And so for the walking leg, the time we spend is the distance that we go when walking. This is walking, not waking, divided by the speed that we go when we're walking. All right, plus, and then the same thing for swimming. So it's the distance we go swimming divided by the speed we go when we're swimming. All right, and hopefully all of these things we can figure out, or write as functions of x. All right, so how about the distance walking? Well, we've already figured that out, actually. That's just 1,000 minus x. And speed walking, well, that's 2. Plus, now the distance for swimming, well, that's this blue distance here. And that's right, we're going to have to use the distance formula because it's a diagonal distance, right? We kind of have a coordinate system going here, and the blue distance is not aligned with the coordinate axis. So we're going to have to use the distance formula. So it's the square root of the horizontal distance, which is x, so x squared, plus the vertical distance, which is 200, so 200 squared. All right, so this is the function that tells us the time that it takes as a function of where we get into the water for swimming. All right, next thing to do is come up with a sensible domain for this problem. So, as a function, this formula is defined for all real numbers, but not every real number is going to make sense as a possible input for this function, right? Just from a realistic standpoint. If you look at the diagram, well, x can't be less than 0, because if x is less than 0, then what that means is we're going to get in the water over here somewhere, but why would we pass by the nearest point to the island? That doesn't make any sense. So 0 is the smallest x value that makes sense. What is the largest x value that makes sense? Well, we are currently standing at x value 1000, and it doesn't make sense for x to get bigger than 1000 because that would mean we would be turning around and walking away from the island before getting in the water and then swimming the whole way. So that definitely doesn't make any sense either. So x has to be less than or equal to 1000. Okay, now it would make sense for x to be equal to 0 because that would mean walking all the way to this closest point and then going straight to the island. And it does make sense for x to be equal to 1000 because that would mean we get in the water immediately, we don't walk at all, and then we swim the whole way. Now it seems unlikely that these 0 and 1000 would produce minimum times, but they're possibilities for x. They're at least sensible possibilities. All right, so now we have a function and we have an interval. Notice that, again, we're in the fortunate position of having a continuous function on a closed and bounded interval. And so the extreme value theorem guarantees that we can find a minimum value, or that there is a minimum value. So we know that minimum value will occur either at a critical point or at one of the endpoints. We kind of suspect that it's not going to be an endpoint, so probably it's a critical point. So let's find a critical point. Let's take a derivative for this function. All right, so let's see, 1000 minus x over 2. Another way to write this is 500 minus 1/2 x. So when we differentiate that part, let's see, the 500 goes away. We're left with minus 1/2 plus, now the derivative of a square root, that's 1 over twice the original square root, so x squared plus 200 squared, which is what? 4 with 4 zeros after it, whatever that is, 40,000. And then don't forget the chain rule. We have to multiply by the derivative of the stuff inside, which is 2x. Now we can simplify a little, so we can get rid of those 2's. All right, so we're left with minus 1/2 plus x over square root x squared plus 40,000. There we go. All right. Well, this derivative function is defined for every real number. We might be worried about dividing by 0, but this denominator is never 0. So this derivative function is defined for every real number x. In particular, it's defined for every x value in this interval that we care about. So there aren't any critical values coming from the derivative being undefined. So we just need to know where's the derivative equal to 0. So let's set it equal to 0. Okay, now let's see. So this is a little tricky to solve because x shows up inside the square root and outside the square root. Why don't we start just by clearing the denominator? So let's multiply both sides of this equation by the square root of x squared plus 40,000. Again, we don't have to worry about the possibility that we're multiplying by 0 because this thing is never 0 for any real number. Okay, so when we clear denominators, we get minus 1/2 times the square root of x squared plus 40,000. Yes, divide it plus x equals 0. This shouldn't be here. All right. Now we're going to have to deal with getting rid of this square root right there. So let's move this x over. Right, that makes this minus x over here. And then also, while we're at it, let's multiply both sides by minus 2, just to get rid of this minus 1/2 right here. So on the left-hand side, we get the square root of x squared plus 40,000. On the right-hand side, we get, let's see, minus x times minus 2 is 2x. Okay, now we can square both sides. We get x squared plus 40,000 equals 4x squared. And now you can see now maybe you can see how we're going to finish solving this. So subtract x squared from both sides. 40,000 equals 3x squared. Then divide both sides by 3. 40,000 over 3 equals x squared. And then take a square root. So x is the square root of 40,000 over 3. Which maybe we can simplify. 40,000 is, oh, that's a perfect square, isn't it? So of course it is, because it came from 200 squared. So this is 200 over root 3. Or if you like to have your denominators rationalized, 200 root 3 over 3. Either one of these is fine, probably. Okay, well, I guess we should be concerned about, right, when you take square roots in an equation, you get plus or minus, but remember, our interval of x values from 0 to 1,000 only included positive x values, so we don't have to worry about the negative possibility here. All right, so we had our endpoint 0, our endpoint 1,000, and then our only critical point, 200 over root 3. Okay, so our the minimum time is one of these values. We just need to figure out which. So we just need to plug each of these values into our original function t of x, which was, what was it, something like 500 minus 1/2 x plus, I don't remember. Uh-oh. I realize now that I didn't put our speed swimming in here. So, oh no. So I'm going to divide, I need to be dividing by our speed swimming, which is 4/5. This is going to change everything. Dividing by 4/5 is the same as multiplying by 5/4. So that's going to put 5/4 right here. Oh man. So now there's a 5/4 right here. So 5/4 right here. So 5/4 right there. Okay, so we'd better throw away this stuff and start at this spot. So we had minus 5/4 x times minus 2. This is going to give us 5/2 x. Okay, and then square both sides. X squared plus 40,000 equals 25/4 times x squared. And then subtract x squared from both sides. 40,000 equals, let's see, that's going to be 21 over 4 x squared. And then, so multiply both sides here by 4 over 21, and we're going to get 160,000. Got an extra 0. There we go, 160,000 over 21 equals x squared. And so our actual value here is Again, I'm going to ignore the negative possibility. This is 400. Do I have one too many zeros here, don't I? Yes. Oh, yes, right. I already scratched out that one. So there we go, 160,000. So square root of 160,000 is 400. Yes, over square root of 21. Okay, and I don't think this simplifies at all, right? Factors of 21 are 3 and 7. Factors of 400 are 2 and 5. Okay. So this should be 400 over square root 21. Okay, now we're back on track. Right. Time spent on our trip is, this is the time spent walking plus the time spent swimming, which is what I had to fix. Here's the time spent. Here is the time spent swimming. So 5 over 4 times the square root of x squared plus 40,000. Okay. All right. So now we can plug in these x values. So at 0, that one is fortunately pretty easy. We get 500 plus 5 over 4 times the square root of 40,000, which is 200. Right, okay. Lost confidence for a second there. But I think this is right. Yeah. Okay. 0 is when we're walking most of the way and then swimming the 200 feet or 200 meters. Yes, okay, so this is right. So 500 plus, let's see, 200 over 4 is 50 times 5 is 250. So 500 plus 250, 750. And that's seconds. Okay. Now let's find the time if x is 1,000. X being 1,000, that's if we get into the water immediately. So we should spend no time walking. And that is reflected in the fact that this first part comes out to be 0 when we plug in 1,000. So, right, good. 0 plus 5 over 4 times the square root of, let's see, 1,000 squared, which is 1,000,000, plus 40,000. Yes. Okay, so 5 over 4 times the square root of 1,040,000, and I will admit that I've sort of reached my tolerance in dealing with things exactly, so I'm just going to punch this into a calculator now. So let's do 5 over 4 times square root 140,000. Sorry, no, 1,040,000. Okay, 1274.75, and this is seconds. No surprise that this is much slower than this, because remember, x equals 1,000 was swimming the whole way, and swimming is slow compared to walking, so no surprise that it's quite a bit longer. Now let's check our critical point, and our critical point was 400 over root 21. Okay, so 500 minus 1/2 times 400 over root 21 plus 5 over 4 times the square root of x squared. So 400 squared is 160,000 over 21. Root 21 squared is 21 plus 40,000. Okay, calculator time again, I think. So 500 minus 0.5 times 400 over square root 21. Let me hit equals on that. Plus 5 over 4 times the square root of 160,000 over 21 plus 40,000. Close my square root, equals, and we get 729 seconds, or 729.12, and yes, that's seconds. So just for the record, maybe we should figure out this 400 divided by the square root of 21. What is that approximately? This is about 87.28, and that's meters because that's an x value. Okay, so looking at these values, we were trying to minimize time, and here's our minimum value for time, right? The other possibilities, these endpoints, were much bigger than that, or somewhat bigger than that in one case. Okay, so what we should do is enter the water when we are 87.28 meters from that point on the shore that's closest to the island. So from the point closest to the island. Right. So with the shore like this, us here, the island there, we're actually, right, remember this was 1,000 meters along the shore to get to this closest point, and we're only going to get into the water 87 meters away from that, so, you know, about here. So we're actually going to walk almost all of the way, and that kind of makes sense because walking is over twice as fast as swimming, so it makes sense to spend more time walking. Now, eventually, the speed savings of just going directly to the island is more than makes up for the sort of taking the detour of to the closest point and then directly, right? So we're going to walk all the way to 87.28 meters from the closest point.